and welcome back. This is lecture 11, where we're going to begin talking about relative humidity and dew point. So up to this point, we've talked about saturation, condensation, evaporation. I introduced all these humidity variables that you've never heard of before and probably will never hear of again. But today we're actually going to talk about the stuff that you have probably seen before and stuff that you've heard on the news and a few interesting implications of it. So again, this is from pages 89 through 98 in the textbook, and let's begin. So I left the last lecture off on a cliffhanger. I began talking about what's called relative humidity. But what actually is relative humidity? Well, it's the humidity variable that you hear on the news, and it's actually the most misleading humidity variable in terms of meteorology. And the reason why is because it's a ratio. Relative humidity is a ratio. And it's actually the ratio of water vapor content. This is how much water vapor is in the air divided by water vapor capacity. How much water vapor can be in the air multiplied by 100%. So let me explain this really quickly with these two things. Water vapor content is, again, how much water is currently in the atmosphere. You can find this out by finding out what the vapor pressure is. Water vapor capacity, on the other hand, is how much water vapor can be in the atmosphere. Here you have to look at the saturation vapor pressure. And the way to figure that out is you need to know what the temperature is. So really, at the end of the day, you can change relative humidity by one of two things. Either change how much water vapor is in the atmosphere or change the temperature. Either increase it or decrease it. And this is where relative humidity can get very tricky. Water vapor content doesn't change as often, but temperature changes all the time. As a result, relative humidity is changing all the time. So again, the way it works is you either increase or decrease the amount of moisture in the air, or you increase or decrease the temperature. Now, with this said, let me talk about what each one of these things does to relative humidity. Well, if you increase the amount of water vapor in the air, that has a direct relationship to humidity. By increasing the amount of water vapor in the air, you've immediately increased the relative humidity. On the other hand, if you decrease the amount of water vapor in the air, so if you did the opposite of what you're seeing on this image, you actually took some water vapor out of the air, you would decrease the relative humidity. So again, adding water to the air increases the relative humidity. Removing water from the air decreases the relative humidity. That one's pretty easy. That one's pretty direct. The other one, however, is a little bit trickier. And the reason why is because water vapor capacity is actually in the denominator of our ratio. And I don't have the time to go back to Math 101 in a way, but just so you know, if you increase the denominator, you've actually lowered the entire value of the fraction. Don't believe me? Write down 1/2 and 1/3. Which one of them is larger? 1/2. So it works like that here as well. By increasing the capacity, you decrease the total relative humidity. You can do this by warming the air up. That's seen down here. Here you have two cases where you have the same amount of water molecules in the air, but you've warmed the air up. By doing that, you've decreased the relative humidity. Because by warming the air up, you've increased the capacity. You've increased the saturation vapor pressure. So in this case, when you warm the air up, you're actually decreasing relative humidity. The opposite is true too. When you cool the air down, you increase the relative humidity. This is one of the reasons why we see dew on the ground in the morning. Because at night, as the air is cooling, it gets more and more saturated. It gets closer to saturation. This allows dew to form on the ground. You don't usually see dew on the ground in the afternoon. Why? Because as you increase the temperature, you've decreased the relative humidity, meaning the air is now less saturated. Now, this actually has a pretty important diurnal variation to it. So this is an activity that I usually use in my classes for groups, and I think it's worth doing it here as well. So here I have a graph showing air temperature. So this is air temperature. How would relative humidity change during this time? Well, to actually figure that out, we need to remind ourselves that when temperature goes up, relative humidity goes down. Why? Because we've increased our capacity. Therefore, we've made the denominator bigger. We make relative humidity smaller as a result. So when temperature goes up, relative humidity goes down. When temperature goes down, relative humidity goes up. So this is how that ultimately ends up looking like on a graph. Here, from midnight to 6 a.m., air temperature is going down. As a result, relative humidity, using this pen here, relative humidity would be going up. Then, as temperature bottoms out at 6 a.m., relative humidity peaks. Then, as temperature goes up, relative humidity begins to go down and down and down until the warmest time of the day, which on this graph is approximately somewhere between 3 and 4 p.m. Then, as the earth cools, relative humidity goes up again until midnight. So, just as a friendly reminder, as temperature increases, relative humidity decreases. And as temperature decreases, relative humidity increases. Okay, so as temperature goes up, relative humidity goes down. As temperature goes down, relative humidity goes up. In our activity this week, you're going to be doing a few examples of this. So it looks something like this. This is what's called the diurnal variation of relative humidity. Notice that as temperature goes down, relative humidity goes up. And typically, when relative humidity is peaking, temperature is usually bottoming out. Now there's other factors that play into this, but we'll keep it at this. And then as temperature peaks up here, that's when relative humidity bottoms out. Now, we actually see this in our everyday life. If you go to a set of observations just for today, so do this for today, go to the National Weather Service, you'll see something that kind of looks like this. What you'll see is an up and down pattern in temperature. Temperature rises during the day, drops at night, rises during the day again, drops at night again, and so on. You see a similar pattern with relative humidity. It drops during the day, rises at night, then drops during the day again, then rises at night. Now, in a few moments, we're going to talk about this other line right down here. This line is what's called the dew point temperature. And we'll talk about it more in a few moments, but let me just say, if you take a look at this line, you notice that it really doesn't move too much. There's a little bit of wiggling, but for the most part, it doesn't change much. This tells us that the amount of moisture in the air hasn't really changed much. As a result, this big up and down motion that you see over here with relative humidity is due to the up and down motion of temperature. Basically, relative humidity is doing the opposite of what temperature is doing. And really, you can see that here. You can even actually notice what almost looks like an upside down pattern. This looks like the upside down version of this. Now, there are other ways we can measure humidity in the atmosphere. I already mentioned them earlier: absolute humidity, specific humidity, water vapor mixing ratio. None of those change with temperature. They only change with content. But relative humidity, on the other hand, changes with both. It changes with both content, how much water vapor is in the air, and capacity, which is determined by temperature. This is why relative humidity is so confusing. Because even if you don't add any moisture to the air, changes in temperature can still cause changes in humidity, changes in relative humidity. So it's a much more complicated variable, and yet it's the one that we use. It's the one that we use. And I think it's because grams per kilogram doesn't really entice people. I think it's because things like grams per meter square don't entice people. I think seeing a percentage is a lot more straightforward. But again, how we get to that percentage is really difficult. Now, how do we actually measure humidity? Well, there's a few different instruments that we can use, but one that you can jerry-rig at home if you wanted to is what's called a sling psychrometer. So let me move ahead in the next slide and then I'll go back to the slide. This is how a sling psychrometer looks like. And a sling psychrometer, as you can see, it has two different thermometers on it. It has one here and one here. And you notice that they're both slightly displaced from one another. The one up here has a little piece of cloth on it. This cloth is called a wick. And what we actually do is we dip this wick into water. Then we pull it back out and we actually swing this whole device around. As we swing the device around, the water on this wick evaporates away. If you recall what we talked about when we did latent heat, that evaporation actually will cool the air around this wick. That causes the temperature of this thermometer to decline. Now we displace the other thermometer so that it doesn't feel those effects. This thermometer is called the dry bulb. This one here is called the wet bulb. Well, after a few minutes, we can calculate what the wet bulb temperature is based on how much it cooled from swinging this thing around, how much it cooled from that evaporation, and we can compare it to the dry bulb temperature. Once we do that, we actually can determine what the relative humidity is using a table. So that's how this process works. So you have a dry bulb, and then you have a wet bulb. You swing the thing around, the water on the wet bulb evaporates, absorbing latent heat into those water molecules, therefore taking heat out of the atmosphere, cooling the atmosphere down. This causes the wet bulb reading to cool down. So that's just one way that we can measure temperature or measure humidity in the atmosphere. Another way is we can use something called a hygrometer, which is basically just a device that's sensitive to changes in humidity. The way that we can use a hygrometer, or the way that a hygrometer works, is we take some object that's sensitive to changes in relative humidity, such as hair. Remember, hair gets curly when it's really moist outside. Well, As a result, when relative humidity changes, that causes these hairs to also change. They either expand as humidity rises, that's what causes the curls to happen, or they contract as humidity declines. We can then take a look at how humidity is changing by as these expand and contract. This causes the needle attached to it to move up and down. Now let's face it, this is kind of an old school machine. We have other things we can use as well, more technological using electricity. We can look at different coils of wire, but this really still gives you a generalized idea of how we can measure humidity using something as simple as human hair. Now the last thing I'm going to talk about in this lecture is dew and how dew forms. Now this was this week's discussion question, so I'm going to try not to give it away too much, but dew point temperature is another key humidity variable. And the good news is it's not as complicated as relative humidity, and it's also often used in weather reports. So it's useful. Dew point temperature is the temperature that air needs to be cooled to in order for it to become saturated. So it's what we have to lower the air temperature to in order for it to become saturated. This is assuming no changes in moisture content, no changes in anything else. This is actually a great indicator of how much water is used or how much water is present in the atmosphere. And in fact, I would rather you know this more than absolute, specific water vapor mixing ratio. Just know that those change only with content. This also changes with content, and it's really a key useful variable. Here's how it works. If you have a high dew point, that means you have lots of water in the atmosphere. So the higher the dew point, the more moisture is in the atmosphere. What this means is that the air is closer to saturation. The higher the dew point, the closer the air is to saturation. The lower the dew point, the less moisture is in the air. Now, unlike relative humidity, this doesn't have a diurnal cycle. This doesn't vary throughout the day. Diurnal again means variation throughout the day. This doesn't cycle up and down throughout the day. It only changes when moisture is either added or taken away from the atmosphere. So there's no diurnal cycle. That makes it a good indicator of how much moisture is in the air because it has no variation. It has no variation. This is useful because when we see something like this where we can see that really the dew point temperature is not changing much. It might bop up and down a degree, but it's not really changing much. As a result, we know that this change in relative humidity is due to temperature changes. It's not due to changes in content. It's solely due to changes in capacity. And so that's why dew point is very valuable to us. It allows us to understand, it allows us to see how much moisture is in the atmosphere. The higher the dew point temperature, the more moisture is in the atmosphere. The lower the dew point temperature, the less moisture is in the atmosphere. Make sure you remember that. Write that down in red ink if you have to. The higher the dew point temperature, the more moisture in the atmosphere. The lower the dew point temperature, the less moisture in the atmosphere. Here's a map showing you the average dew point temperatures around the continental United States during winter time. If you can notice, areas such as, let me get my cursor here, areas such as Fargo, North Dakota, over here in Nevada, and much of the inner part of the United States is really dry. This area up here is really dry. Meanwhile, down here, where temperatures are a lot higher, dew point temperatures are a lot higher. Here you see dew point temperatures in the 40s, 50s, and 60s. Down here, the air is a lot wetter. Right? So the air is a lot wetter where dew point temperatures are higher. It's a lot drier where dew point temperatures are lower. Now if you take a look in the summer months, you notice dew point temperatures are substantially higher. They were very low in the wintertime, very high in the summer months. The reason why this happens is because there's more evaporation in the summer months. Hence, more evaporation means more moisture in the air. More moisture in the air means higher dew points. If you take a look over here, pretty much the entire eastern seaboard is very wet. Meanwhile, over here, the desert southwest is much drier. Sorry about that. It's much drier over here, much wetter over here. Now, how does dew form? Well, I'm not going to give you the full answer because, again, it's our discussion question, but let me give you a 30-second kind of guess. At nighttime, as air temperature cools, this allows the air to become very close to saturation. Now, if you recall from last week's module on air temperature, near the surface of the Earth, the air can become much colder than just a few feet above it, than just a few meters above it. As a result, surfaces near the ground, such as grass, vegetation, or even your car, can lose a lot more heat than the surrounding air. Therefore, they become much colder and oftentimes reach saturation. Now, if you remember, the opposite happens during the daytime. During the daytime, the area near the ground becomes very hot. Therefore, it's the least saturated. During the nighttime, the air near the ground is very cold, therefore it's very saturated. During the daytime, the air near the ground and near surfaces is very hot. Therefore, it's the least saturated. Now, there are some times where the dew point can be below freezing, and the temperature that the air is can be below freezing. This leads to what's called frost. Here's how dew looks like, and here's how frost looks like. So in this case, you still get that water that forms on those surfaces as the air becomes saturated, but because the temperature is below freezing, all that water instead freezes into frost. It looks like almost like a white glaze in a way, and it's really beautiful to look at in the morning, and we get it pretty commonly here in the Bay Area during the winter time. So if it's winter out there right now, go outside and take a look. Otherwise, wait till winter time and take a look. All right, that's enough for today. That's enough for this lecture. So we'll cover some more stuff next time on clouds. Until then, I'm Terrence Mullins. Thank you for watching, and please feel free to go back and review as much as possible. If you have questions, please email me. Don't hesitate to ask for help. All right, we'll see you next time.